welcome to this problem walkthrough. Today, we'll explore an interesting graph theory question titled Graph Connectivity with Threshold. We'll discuss the problem, break it down, and look at intuitive approaches to solve it. Let's dive in. In this problem, we're working with an undirected graph that has n nodes, labeled from 1 to n. You are given a threshold value and a set of queries. Each query asks whether two specific nodes in the graph are connected. The key condition for connectivity is that every edge in the path between the nodes must satisfy a greatest common divisor, or GCD, condition. Specifically, the GCD of the two endpoints of each edge must be greater than the given threshold. The goal is to determine the connectivity of the nodes for each query and return the results as a Boolean array, where true means the nodes are connected and false means they are not. This setup provides an interesting challenge involving both graph traversal and number theory. The output for this problem is a list of Boolean values, one for each query. Each value represents whether the two nodes in the corresponding query are connected based on the GCD condition. To better understand how this works, let's look at an example. Suppose n is 6, the threshold is 2, and the queries are 1, 4, 2, 5, 3, 6. For the first query, 1, 4, the GCD of 1 and 4 is 1, which is not greater than the threshold of 2, so nodes 1 and 4 are not connected. The result for this query is false. This demonstrates how the threshold limits the connectivity of nodes based on their GCD. Now, for the second query, 2, 5, the GCD of 2 and 5 is also 1, which again does not exceed the threshold of 2. Therefore, nodes 2 and 5 are not connected, and the result is false. For the third query, 3, 6, the GCD of 3 and 6 is 3, which is greater than the threshold of 2. This means nodes 3 and 6 are connected, so the result is true. In another example, with n equals 6 and a threshold of 0, all nodes are effectively connected because any positive GCD is greater than 0. For queries like 4, 5, and 3, 6, the output is true for both, illustrating how a lower threshold increases connectivity. In the next example, consider n equals 5, a threshold of 1, and queries 4, 5, 1, 2, 2, 3. For the first query, 4, 5, the GCD of 4 and 5 is 1, which is equal to the threshold but not greater than it. Therefore, nodes 4 and 5 are not connected, resulting in false. Similarly, for the queries 1, 2, and 2, 3, the GCDs of the respective pairs are also not greater than 1. Thus, all queries return false. This example highlights how increasing the threshold restricts connectivity, as fewer pairs of nodes satisfy the GCD condition. To summarize, the problem has constraints that must be taken into account. The number of nodes, n, ranges from 1 to 10,000, and the threshold lies between 0 and n1. Each query involves two distinct nodes, and the number of queries can go up to 10,000. Certain edge cases are worth noting. When the threshold is 0, all nodes are connected because any positive GCD satisfies the condition. On the other hand, when the threshold is very close to n, connectivity is highly restricted, as very few pairs of nodes will have a GCD greater than the threshold. Finally, with a single query, the output is simply a single Boolean value, making it a minimal case to handle. To begin, the brute force approach is the most straightforward way to solve this problem. The intuition here is to directly check the connectivity between every pair of nodes u and v for each query. The key condition for connectivity is that there must exist a path where all nodes along the path share a common divisor greater than the threshold. To achieve this, we would iterate over all pairs of nodes and explicitly construct paths based on their divisors. However, this approach comes with significant challenges. First, two nodes can only share an edge if their greatest common divisor, or GCD, is greater than the threshold. While this observation helps, the process of checking divisors and constructing valid paths for every query becomes computationally expensive. The time complexity is O, n squared plus q, where n is the number of nodes and q is the number of queries. The O, n squared, term comes from the graph construction, which involves iterating over all pairs of nodes, and the O, q, term accounts for checking the queries. While this approach is simple to implement, it is inefficient for large inputs, making it impractical when n grows to values as large as 10 to the power of 4. Now, to address the inefficiencies of the brute force approach, we turn to the optimized union find method. This approach leverages a disjoint set union data structure, or DSU, to represent connected components without explicitly constructing the graph. The key idea is to group nodes into components based on their shared divisors greater than the threshold. Here's how it works. Starting from threshold plus 1, we iterate through all potential divisors. For each divisor D, we connect all of its multiples into the same component using union find operations. This eliminates the need for pairwise checks in graph construction. Once the union find structure is built, answering queries becomes highly efficient, as we can simply check if two nodes U and V belong to the same component using the find operation, which runs in nearly constant time. The steps are straightforward. Initialize union find for all n nodes, link all multiples of each divisor greater than the threshold, and finally, process each query to verify connectivity between nodes. This drastically reduces the computational overhead compared to the brute force method. The time complexity of the union find approach is O, n log n plus q. The O, n log n, term comes from processing all divisors and connecting nodes, while the O, q, term accounts for the query checks. This efficiency makes the method suitable for large inputs, even when n is as big as 10 to the power of 4. Additionally, the memory usage is linear, requiring O, n, space. There are trade-offs to consider, though. While this method is highly efficient, it does require an understanding of the union find algorithm. However, with standard templates and libraries available, the complexity of implementation is manageable. For this problem, the union find approach is the clear choice. It scales well for large values of n, allows for constant time query responses after pre-processing, and eliminates the need to explicitly construct the graph. The key insight lies in recognizing that we can group nodes based on shared divisors greater than the threshold, significantly improving performance and reducing computational effort. Finally, let's reflect on why the brute force approach is not ideal. The main issue is its inefficiency for large n due to the O, n squared, time complexity required to construct the graph. Additionally, storing all edges explicitly introduces unnecessary memory overhead. On the other hand, the union find approach leverages mathematical properties of divisors to pre-process connected components efficiently. By avoiding explicit graph construction and directly grouping nodes based on shared divisors, it handles the problem in a much more scalable way. This makes union find the superior choice, both in terms of computational efficiency and practical feasibility for large inputs. By focusing on the threshold condition and using an optimized data structure, we achieve a solution that is not only faster but also more elegant, addressing the problem's constraints effectively. To solve this problem, we aim to determine if two nodes in a graph are connected by a path where all nodes along the path share a divisor greater than a given threshold. This boils down to checking connectivity under specific conditions. The first step in our algorithm is pre-computing divisors for all numbers up to the maximum node value, which we call max_val. Using a mapping, each divisor will point to the list of numbers divisible by it. This grouping is essential because nodes sharing a divisor could potentially form connected components. Next, we filter these groups by removing nodes less than or equal to the threshold, as they cannot contribute to a valid path. This step ensures we only process nodes that are relevant. Finally, we use a union find data structure to group nodes dynamically based on shared divisors, efficiently managing and merging connected components as we process the data. After filtering nodes based on the threshold, we process each divisor and the corresponding filtered nodes. For these nodes, we use union find operations to merge them into the same connected component. The two key operations in union find are find, which identifies the root or parent of a node, and union, which merges two components when nodes share a divisor. We optimize these operations using path compression and union by rank to make them nearly constant time, specifically O, alpha, n, per operation, where alpha is the inverse Ackermann function. Once all components are formed, answering the queries becomes straightforward. For each query, we simply check if the two nodes belong to the same connected component. If they do, we return true, otherwise, false. The efficiency of union find ensures that each query is processed quickly. By combining divisor pre-computation, dynamic connectivity management, and optimized processing, we arrive at a scalable solution. To implement the algorithm, we rely on two key data structures. The first is a mapping of divisors, where each divisor maps to a list of numbers divisible by it. This allows us to group nodes efficiently as we process the graph. The second is the union-find data structure, which is critical for dynamically managing connected components. Together, these structures enable us to handle the problem efficiently. The complexity of the algorithm is as follows. Pre-computing divisors takes O, max_val asterisk log, max_val, as we enumerate divisors for all numbers. Union operations take O, n asterisk alpha, n, where n is the number of nodes greater than the threshold. Query processing takes O, q asterisk alpha, n, where q is the number of queries. The overall complexity is dominated by divisor pre-computation and union-find operations, making it feasible for large inputs. We also address edge cases such as when all nodes are below the threshold, where no valid paths exist, or when thresholds are very large, which reduces the number of nodes to consider, further optimizing the computation. Let's walk through an example to see the algorithm in action. Consider nodes 2, 3, 4, 6, 9, with a threshold of 2 and queries 3, 6, 4, 9. First, we generate the divisor mapping, nodes divisible by 1R, 2, 3, 4, 6, 9, by 2R, 2, 4, 6, and by 3R, 3, 6, 9, and so on. Next, we filter out nodes less than or equal to the threshold, leaving us with 3, 4, 6, 9. Using union find, we process each divisor. For divisor 3, nodes 3, 6, 9 are merged union 3, 6, and union 6, 9. For divisor 4, nodes 4, 6 are merged union 4, 6. Finally, we answer the queries. For 3, 6, we find that both nodes belong to the same component, so the result is true. For 4, 9, they belong to different components, so the result is false. This example highlights how the algorithm efficiently groups nodes and processes queries. In conclusion, this approach effectively addresses the problem by combining divisor pre-computation, threshold-based filtering, and the union-find structure. It scales well for large inputs due to its efficient handling of dynamic connectivity checks. By focusing only on nodes greater than the threshold, we minimize unnecessary computations, ensuring the algorithm remains optimal even with high thresholds or large graphs. The union-find operations, enhanced with path compression and union by rank, provide nearly constant time performance for merging components and answering queries. Together, these techniques create a robust solution that is both scalable and capable of handling edge cases seamlessly. Here, we start by importing the greatest common divisor function from the math module, as it will be useful for determining relationships between nodes. Inside the solution class, the main function rConnected takes 3 parameters: the total number of nodes n, the threshold, and a list of queries to process. The first condition checks if the threshold is 0. If it is, all nodes are considered directly connected, so we immediately return a list of true values for all queries. Next, we define a parent list to represent the union-find data structure, where each node is initially its own parent. To optimize union-find operations, we implement a find function with path compression. This ensures that when searching for the root of a node, we flatten the tree structure, making future searches more efficient. The union function then merges 2 disjoint sets by pointing the parent of one root to the other, effectively joining the 2 sets. Now, we iterate through all numbers greater than the threshold up to n. For each number, we identify its multiples within the range and use the union function to connect them. This step ensures that nodes sharing common divisors larger than the threshold are grouped together in the same connected component. After preparing the union find structure, we process the queries to determine connectivity between pairs of nodes. We initialize an empty list called result to store the answers for each query. For each pair of nodes u and v in the queries, we use the find function to check if both nodes belong to the same connected component. If they do, we append true to the result list, otherwise, we append false. Finally, we return the result list as the output, which contains the connectivity status for all the queries. This implementation efficiently handles the problem by leveraging union find and optimizing it with path compression, ensuring that the solution scales well even for larger inputs. Here, we start implementing the solution to the problem in Java. First, we define the class and the main method, rConnected, which accepts 3 parameters: the number of nodes n, a threshold value, and a list of queries. If the threshold is 0, it means all nodes are considered connected regardless of their values. In this case, we create a result list, mark every query as true, and return it immediately. Now, to handle cases where the threshold is greater than 0, we initialize a union find structure. This involves creating a parent array that keeps track of the representative or root node for each node. Initially, each node is its own parent, so we populate the array accordingly. Next, we implement the find function, which uses path compression to efficiently determine the root of a node. If a node is not its own parent, we recursively find its root and update the parent array to point directly to this root, optimizing future queries. We then define the union function, which connects two nodes by merging their respective sets. This is done by finding the roots of the two nodes and updating the parent of one root to point to the other, effectively merging the sets. Once the union find functions are ready, we proceed to connect nodes that share common divisors greater than the given threshold. Starting from threshold plus 1 up to n, we iterate through multiples of each number and connect them using the union function. This ensures that all nodes with a common divisor greater than the threshold belong to the same connected component. Finally, we process the queries. For each query, we retrieve the two nodes and check if they share the same root using the find function. If they do, we add true to the result list, otherwise, we add false. Once all queries are processed, we return the result list. This completes the implementation of the solution. In this example, we are given n equals 6, a threshold of 2, and 3 queries, 1, 4, 2, 5, and 3, 6. First, we initialize the union find data structure by creating a parent array where each node is its own parent. This means the parent array starts as 0, 1, 2, 3, 4, 5, 6. We also define the helper functions find for path compression and union to merge two sets. Next, we focus on connecting nodes that share common divisors greater than the threshold. Starting with I equals 3, threshold plus 1, we find that 6 is a multiple of 3. Calling union 3, 6, we see that 3 and 6 have different roots, so we update the parent of 3 to point to 6. The updated parent array becomes 0, 1, 2, 6, 4, 5, 6. For I equals 4, I equals 5, and I equals 6, there are no multiples greater than the threshold, so no further unions are performed in this step. Now, we process the queries using the union find structure. For the query 1, 4, we check the roots of nodes 1 and 4 using the find function. Since their roots are different, they are not connected, so we append false to the result. For the query 2, 5, we again find that nodes 2 and 5 are not connected, so another false is appended. For the query 3, 6, we find that both nodes share the same root, meaning they are connected, so we append true. This gives us the final output of false, false, true. Moving to the second example, we have n equals 4, a threshold of 0, and two queries, 1, 2, and 3, 4. With a threshold of 0, all nodes are considered directly connected since there are no restrictions. This means both queries return true, resulting in an output of true, true. In this third example, we have n equals 8, a threshold of 3, and 3 queries, 4, 8, 6, 9, and 7, 8. We begin by initializing the parent array as 0, 1, 2, 3, 4, 5, 6, 7, 8. Next, we connect nodes that share common divisors greater than the threshold. Starting with I equals 4, we find that 8 is a multiple of 4. Calling union 4, 8, we update the parent of 4 to point to 8, resulting in the updated parent array 0, 1, 2, 3, 8, 5, 6, 7, 8. For I equals 5, I equals 6, I equals 7, and I equals 8, no multiples greater than the threshold exist, so no further unions are performed. Finally, we process the queries. 4, 4, 8, both nodes share the same root, so they are connected, and we append true. For 6, 9, the nodes are not connected, so we append false. Similarly, 4, 7, 8, the nodes are not connected, so we append false. This gives the final output of true, false, false. To analyze the time complexity of our solution, we can break it down into 3 distinct parts: initializing the union find structure, connecting nodes based on divisors, and answering the queries. First, initializing the union find structure involves creating the parent list, which is simply a one-time operation that requires n time, as the list has a size of n plus 1. Next, we focus on connecting nodes based on their divisors. For each integer I starting from threshold plus 1 up to n, we iterate over its multiples. For each multiple, we perform a union operation to connect the respective nodes. The number of multiples for any I is roughly n divided by I, and when summed across all integers greater than the threshold, this iteration count is approximated by a harmonic sum. Since harmonic sums grow logarithmically, the total number of iterations is bounded by n asterisk log n. Additionally, each union operation requires finding the roots of the nodes, which has an amortized complexity of alpha n, where alpha n is the inverse Ackermann function and grows extremely slowly. Combining these, the time complexity for this step simplifies to n asterisk log n. Now, let's discuss the third component, answering the queries. For each query, we check if two nodes are connected by performing a find operation on their roots. The find operation has an amortized complexity of alpha n, which remains very efficient even for large inputs. For q queries, the total time complexity for this step becomes q asterisk alpha n. When we combine all three parts, the overall time complexity is n for initialization, n asterisk log n for connecting nodes, and q asterisk alpha n for queries. Since alpha n grows so slowly that it can be treated as nearly constant, the overall time complexity is dominated by n asterisk log n for the union operations and q for the queries. As a result, the final time complexity of the algorithm is n asterisk log n plus q, which is highly efficient given the problem constraints. Shifting focus to space complexity, the primary factor to consider is the storage requirements of the union find structure. The parent list, which tracks the nodes' relationships, has a size of n plus 1, leading to a space requirement of n. Beyond this, the algorithm does not rely on any additional data structures, apart from variables used for the loops in query processing, which do not contribute significantly to the space usage. Thus, the overall space complexity of the solution is n, making it very space efficient. Lastly, let's compare this optimized approach with the brute force method. A naive solution would involve explicitly checking the connectivity of all pairs of nodes for each query. This would require iterating through all pairs to build connections, resulting in a time complexity of n squared for constructing the graph and q for processing the queries, giving a total time complexity of n squared plus q. The space complexity of the brute force approach would still be n, due to storage requirements for the graph structure. In contrast, the optimized solution leverages the union find data structure and efficient divisor-based iteration, reducing the time complexity to n asterisk log n for building connections while keeping the space complexity at n. The key mathematical insight here is the use of harmonic sums, which grow logarithmically, allowing us to achieve n asterisk log en complexity for the divisor-based iteration. Additionally, the nearly constant time performance of union find operations due to path compression ensures efficient query processing. Together, these improvements make the optimized solution far more scalable, especially for large input sizes, where the brute force approach would quickly become impractical. When working on this problem, there are a couple of common mistakes to watch out for. One frequent issue is failing to optimize for multiple queries. If you recompute connectivity from scratch for every single query, the solution can become very inefficient, especially when the number of queries is large. This approach often leads to time limit exceeded errors. To address this, you should use a pre-processing step, such as building a union find data structure, which allows you to handle multiple queries efficiently. Another mistake is incorrectly handling the threshold condition. Some solutions only check whether the immediate nodes, u and v, meet the threshold, without considering the intermediate nodes along the path. This can result in incorrect results because all nodes on the path must satisfy the threshold condition. Be sure to account for this when implementing your solution. Another challenge developers face is overlooking edge cases. For example, graphs with isolated nodes can behave differently than expected, or threshold values larger than any node value can make all nodes disconnected. Additionally, queries where u equals v might require special handling to ensure correctness. To prevent surprises, it's important to test your solution with a variety of corner cases. Inefficient graph construction is another common pitfall. Using adjacency matrices for large graphs can lead to excessive memory usage and slower edge-based traversal. A better alternative is to use adjacency lists, which are more efficient in terms of both speed and space. Finally, misunderstanding how to use union find can lead to slower performance. If you forget to implement path compression and union by rank, the union find operations can become inefficient, especially for large graphs with deep trees. Including these optimizations ensures that operations run in near constant time. In interviews, one of the key insights for solving this problem is recognizing the importance of pre-processing. Efficiently handling multiple queries often depends on preparing the graph in advance, such as using union find or shortest path algorithms. Another valuable strategy is to look for patterns. Problems involving thresholds or constraints often require filtering edges or nodes before solving the main problem. Understanding how these constraints affect the graph structure is critical. When evaluating different approaches, it's important to weigh the trade-offs. For instance, a brute force solution might be simpler to implement but becomes impractical for large inputs. On the other hand, using union find with threshold filtering is much more efficient, with time complexity proportional to the number of nodes, edges, and queries. Alternatively, you could use depth-first or breadth-first search for each query, which is flexible but slower compared to union find, particularly when queries are repeated. To deepen your understanding of this problem, you can explore related problems that build on similar concepts. For instance, LeetCode 323, which focuses on finding the number of connected components in an undirected graph, is an excellent opportunity to practice union find in depth-first search approaches. LeetCode 684, on redundant connections, introduces cycle detection using union find, which is highly relevant. Another interesting variation is LeetCode 839, which deals with similar string groups. Here, connectivity is determined by string similarity, providing a higher-level application of union find. Finally, LeetCode 1202, smallest string with swaps, demonstrates how union find can be applied to grouping and rearranging elements based on connectivity. These problems not only reinforce the core concepts but also expose you to different ways of applying them. There are several alternative approaches to solving this problem, each with its own advantages and trade-offs. Using depth-first or breadth-first search for each query is straightforward and works well when the graph is sparse or the number of queries is relatively small. However, this method can become inefficient for larger graphs or when there are many queries, as it repeatedly recomputes connectivity. A more efficient option is to use union find with pre-processing. This approach is particularly effective for large graphs with many queries, as the pre-processing ensures that subsequent queries can be handled almost instantly. The downside is that it requires additional memory for the union find data structure. Another approach is to use modified Dijkstra's or Floyd-Warshall algorithms. These are useful for weighted graphs and can handle shortest path calculations, but they are often overkill for unweighted connectivity problems and have higher time complexity. Ultimately, the key takeaway is that pre-processing the graph to optimize query handling is usually the best strategy. Union find is a powerful tool for efficiency, but always consider the specific constraints and edge cases of the problem at hand. Great work! Today, we discussed the graph connectivity with threshold problem and reviewed an intuitive brute force approach. We learned about graph connectivity queries and the importance of efficiency in large datasets. Thanks for joining, and see you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!